Hello everyone, welcome to the video. Today we are going to discuss the problem longest palindromic subsequence. In this problem, we are given a string as an input and we have to return the length of the longest subsequence in this string, which is also a palindrome. We'll go through the thinking process for this problem, we'll write the algorithm and we'll also see the code for it. If you are new to the channel, please don't forget to subscribe. Let's start. To begin with, let us first note down the key things given in the question. We are given a string s and we have to return the length of the longest palindromic subsequence in this string. For example, if this is the string given to us, then the length of the longest palindromic subsequence is 4. How? These 4 b's, these form a subsequence, they are a palindrome and they are the longest possible such palindromic subsequence, and hence the answer is 4. So if we consider our solution as a black box, we are getting input as string s and we are returning an integer length as output. So what will our function signature look like? Our function signature will look something like this. Before even attempting the problem, let us first try to understand what is a subsequence. From the example given here, what can we infer? The first thing that we can infer is that subsequence is basically some sequence of characters from the given string. What else can we infer? We can see that the characters in the subsequence are in the order in which they are present in the same string. Example, AB is a subsequence, but BA is not. The third thing that we can infer is that these characters that we pick, they may not necessarily be contiguous. For example, AC is also a valid subsequence. These three conditions together applied on a string will give us the definition of a subsequence. Now, our aim in the problem is to find the longest palindromic subsequence of that string. So what can be the simplest approach that we can think of? One way is that we get all possible subsequences of this string. We iterate over them, all of them, and then we check for every subsequence whether this is a palindrome. If this is a palindrome, then we will know its length and we will maintain whatever is the max length seen so far. What does that mean? That means whenever we find that this subsequence is a palindrome, we'll check if its length is greater than the max length so far. If it is, then we will update the value of this variable. And finally, when we are done with all the iterations, we will return max length so far. And getting all possible subsequences of a string, we will collect them in a set of string. So if we go through this algorithm and we return the max length so far, we will get the length of the longest palindromic subsequence. Now we have only two things remaining. First is, how do we get all possible subsequences of a string? We have discussed this problem in our past videos where we take our input as a string and we return all possible subsequences of that string in a set as output. You can find the link to both of these videos in the description as well as in the top right corner of your screen. The second problem that we have is that how do we check if a string is a palindrome? This problem is a pretty straightforward one, where we just start from the start and the end of that string and we keep matching the characters till we reach the middle. With this, we can solve this problem using this whole of the algorithm and get our answer. But what will be the time complexity of this problem? The time complexity will be exponential. Why? Because this step in itself takes exponential time. Since this is very high, we need to think of an alternative approach. Before going to approach 2, let us try to make a very simple observation regarding this problem. In this problem, we are given a string and we have to find the length of the longest palindromic subsequence. Now let's say whatever that subsequence is, that subsequence will also be present in the reverse of this string. That is a fair statement to make. We can see here in the example that we have reversed this string. Now even in the reversed string, the subsequence BBBB is present, which was also present in the original string. So what can be the approach to solving our original problem, longest palindromic subsequence? We can have the string S. We can reverse the string S dash, and then we find the length of the longest common subsequence between S and S dash. That will give us the longest palindromic subsequence in S. Now, reversing a string is a very simple problem that we can do. But how do we find the length of the longest common subsequence between two strings? We have discussed this in the past videos, where we take two strings as input and return the length of the longest common subsequence. We have solved this using top-down dynamic programming as well as bottom-up dynamic programming. You can find the link to both of these videos in the description as well as in the top right corner of your screen. With this approach, we can solve the problem of longest palindromic subsequence. Now, what will be the time and space complexity of this approach? Its time complexity will be big O of n square because this step will take big O of n square time. Its space complexity can be big O of n square or big O of n depending upon the approach we have implemented. But this approach overall of longest common subsequence is difficult to think of if we have not solved a longest common subsequence problem earlier. It is difficult to get the intuition for this. So let us see another approach to solving this problem. Since we cannot think of any other straightforward method to solve this problem, let us see if we can solve this problem using recursion. That means we will have to break our problem down into smaller problems. How do we break it down into smaller problems? We are talking about the palindromic subsequence here. So let us say that the first case of our example is that the first and the last characters of the given string are same. Now, if somebody tells me the answer to this middle portion, except the first and the last character, that means somebody tells me that m is the length of the longest palindromic subsequence for this middle portion. Can I use this answer m to derive the answer for this whole of the string? I don't care how this m was calculated, but can I use this m to derive the answer for the whole? Yes, the answer for the whole will be m plus 2 because we will add 2 more characters to m. So here we were able to use the answer to a smaller problem to derive the answer to the larger problem. Why are we calling this a smaller problem and this a larger problem? Because the length of the input here is smaller as compared to the length of the input for the original problem. But this was the case where first and last characters were same. But in our input, we can get a string whose first and last characters are not same. Example, this string. How will we break the problem then? Obviously, this B, first B and last C cannot be part of the longest palindromic subsequence. So let us say somebody gave us the answer to this problem, this part. Somebody said that the longest palindromic subsequence in this part, length of it is n. Can we use this answer to derive the answer for the whole string? Yes, if the length of the longest palindromic subsequence for this part is n, then C cannot be added to that longest palindromic subsequence. So the answer for overall will also become n. But this was just one way of breaking the problem down. Instead of excluding the last C here, we could have excluded the first B. And now, if somebody gives us the answer to this part and says that the length of the longest palindromic subsequence in this part is O, then what will be the answer for the overall? Answer for overall will also be O. But then, what should be my answer for this string, N or O? Since we are looking for longest, whatever is maximum of the two, that should be my answer. So what we have essentially done here is, we have seen how answers of smaller problems can be used to derive the answer for the original problem. Now let us see how will we represent all of these problems, our original problem and all of our smaller problems in one common manner. So if we are representing our original problem as LPS of string I, j, where I is pointing to our starting letter and j is pointing to our last letter. Then how will we represent this problem? This will correspond to I plus 1 comma j minus 1, and this will correspond to I comma j minus 1, and this will correspond to I plus 1 comma j. So LPS of si comma j will become equal to this. This is our recursive relation. So what we have done here is we have represented our original problem into in terms of answers of our smaller problems. One thing to note here is that we are given only one string as an input in our original problem. We are not given some I or j. We need I comma j here in the recursive relation. That means this will be a separate method that we will call from our original method. With this recursive relation in mind, let us now try to write the algorithm for the problem. So this is our recursive relation that we have derived in the previous step. So with this, we have completed the first step of solving any recursion problem. We have the recursive relation. We have also identified the inputs that will go into the recursive method. The inputs are string s, int I, and int j. This is our utility method that will be called recursively. That means this will keep calling itself. And we will call it initially with our string s as input, i's value will be 0, and j's value will be n minus 1, where n is the length of the string. So this is how we will call it initially. Now let us try to write the algorithm as per this recursive relation. So as per the recursive relation, if the two characters at the start and the end are equal, then our answer will be LPS util of si plus 1 j minus 1 plus 2. And if they are not equal, then our answer will be maximum of the two, LPS util si j minus 1 and LPS util si plus 1 j. But is this method complete? Will this work? No. Why? Because this method is calling itself. So when we call with I comma j, it will call here, and then it will keep on calling itself again and again. It will never end. It will go into an infinite loop. So we need something called as base or terminating condition of this recursion. And when will the base or terminating condition arrive? When the input will be lowest. And what will be the lowest input possible here? The length of the string, relevant part of string, becomes 1, or the length of the relevant part of string becomes 2. How will we represent the one length string in terms of I and j? If the length of the string is 1, then I will be equal to j. Since there is only one character, what will be the length of the longest palindromic subsequence in such a string? It will be 1, since that character is the palindrome. And if the length of the relevant part of string is 2, that means j minus I is equal to 1, then our answer can be 1 or 2, depending on what are the characters for the two length string. If the characters are different, like a, b, then the longest palindromic subsequence can be either a or b, so our answer will become 1. But if the characters are same, like a, then the longest palindromic subsequence will become itself, so our answer will be 2. Now one thing to note here is that for the base or terminating condition, why did we go till length 1 and length 2? Why did we not stop at length 1 itself? It is because in the recursive relation, we can see that the length of the input for smaller problem can be lesser than the length of the input for original problem by 1 or by 2. Here I to j minus 1, this length will be lesser by 1 than I to j, while I plus 1 to j minus 1, this length will be lesser by 2 as compared to I to j. And hence in our base conditions, we include both lengths 1 and lengths 2. Because consider if we had only included length 1 and here we were at, let's say, length 2, then it is possible that for solving this length 2, we would have gone to length 0. Then recursion would have never ended. That is why in the base condition we are taking both length 1 and length 2. Now this is a perfectly working solution. It will work just fine and will return us the length of the longest palindromic subsequence. But its time complexity is very high. Why? Because it has some overlapping and duplicate subproblems. And we are solving these overlapping and duplicate subproblems multiple times. How? Let us say we started at LPS 0, 6. Now as per this recursive relation, it will be dependent on LPS 1, 5, LPS 0, 5 and LPS 1, 6. If we further expand this recursion tree in all of the three branches, then we will see this something like this. Now here we can see many overlapping problems. For example, LPS 1, 5 is mentioned thrice. LPS 1, 4 is mentioned twice. LPS 2, 5 is also mentioned twice. Now it is a very small input. If the input was very large, then we will see many more numbers of overlapping problems, and each overlapping problem will be repeated multiple times. Now calculating for these again and again is inefficient. We have to solve this problem. How do we solve it? We can simply do one thing. Whenever we encounter one input, for example, we encountered 1, 5, we solve it and we store its answer somewhere, like in a map. And when we encounter the same input again, then we don't solve it completely. Instead, we check if we have found this input in the map. If we have, that means we have already solved it. So we return the answer from the map directly. And that is what we will use here. So what information will our map store? It will store that for a pair of I, j, this is our answer. So what will be the data types of key and value in the map? Value is definitely very simple, integer, because answer will be the length of the longest palindromic subsequence. Our key should be able to represent I, j. Now we can use string to represent I, j as key. How? We can use I and j to form a string like this, I underscore j. For a pair of I, j, this will be unique. So our map will be of type string, integer. Let us see how does our algorithm change with the introduction of map. We will now have a new argument to this function, a map of string and integer. So wherever we have called this function, we will pass in the map. Then before returning our answers, we will put them in the map that hey, for this key, this was our answer. And now before solving, we will first check in the map if this key was present. If this key was present, we will return the answer directly from the map instead of solving this again. This is now a perfectly working solution for longest palindromic subsequence problem. What will be the time complexity of this? The time complexity will be big O of n square. Why? Because we are solving for a pair of I, j only once and exactly once. Therefore, I and j can take maximum of n and n values. So overall time complexity will be big O of n square. And similarly, space complexity will also be big O of n square. Let us now see the working code for the same algorithm that we just discussed. You can also find the link to this code in the description. So first of all, we find the length of the string and we also declare a map of string, integer. Then we call this utility function with s and initial value of I as 0, initial value of j as n-1 and the map. This will be the function that will be called recursively. Now here in this method, what we do, first of all, we write the base conditions. If the length of the relevant string is 1, that means if I and j are equal, then that character is already a palindrome. So we return 1. If the length is 2, that means j minus I is equal to 1, then we check if the two characters are equal. If the two characters are equal, then we return 2. Otherwise, we return 1. Now we are done with the base condition. So first of all, we build the key using I, j. What do we mean by key I, j? It is simply I underscore j. We build this using this separate function. Once we have built the key, we check this or we try to find this key in the map we want to see if we have seen this problem earlier itself. If we find that in the map, then we return the answer directly from the map instead of solving further. But if we don't find in the map, then we go and solve using recursion. So if again we first check that if the two characters are equal. If the two characters are equal, then our answer is the answer for the middle portion plus 2. But before returning the answer, we put that in the map so that we can use it whenever we encounter the same input again. If the two characters were not equal, then we calculate the two candidate answers. One excludes the last character and second one excludes the first character. And whichever is the maximum of the two is our answer. But again, before returning the answer, we put that in the map. So this is the code for longest palindromic subsequence using memoization or top-down dynamic programming. This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also, let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.